In this video, we will show how to design photonic structures where the final layer is a thin layer of metal, but, nevertheless, these structures can support the long-range propagation of optical waves over their surfaces. In the previous video, in structure without metal, we could arbitrarily set both the wavelength and the excitation angle. Here, in a structure with the final metal layer, we can still set any wavelength, but the excitation angles should be within a small range of angles from the angle of total internal reflection to an angle of about ρ1/2, which depends on the thickness of the metal film. Let us set the film thickness and calculate what angle should be set to support long-range propagation of surface plasmons. This angle is about of 1.003. We can see that when we set this angle, the polarization was switched to P due to the presence of the metal layer. And now we can, like the last time, set the Sellmeier formulas for the double layers and calculate the thickness. The program gives us both the thickness D1, D2 of the double layers and the possible thicknesses D3. We pass to step 2 and now we need to choose the optimal number of layers for P polarization. The optimal number of layers for P polarization is always greater than for S polarization because P polarization has a Brewster angle for reflection between the double layers. At Brewster angle the reflection disappears and the band gap becomes narrower near this angle. We see that for given imaginary parts and for given losses of metal in the structure, we have this number of layers as optimal, since the resonant dip in reflection reaches almost zero. We have a resonant dip near ρ equals 1.003 and a propagation length of 165 m, which is quite a lot for a metal film. Let's see, where is the resonant wavelength? Here we see that we do indeed have a resonant wavelength for this structure equals 633 nanometers. And now we can see the spatial distribution of the field in this structure. All hints for shortcuts can be found here. The field distribution is such that the zero field is at the center of the metal film, which minimizes losses in the metal film. We can take a closer look at it, leaving, say, the last 4 layers. It can be seen again that the metal film has zero fields, as expected, in the center of the metal film. Now let's see the dispersion of this structure. We see the band gap and see the surface mode exactly where it was expected to be. We can also change the metal to a more damped one, such as palladium, if, for example, we want to make a hydrogen sensor. Now, looking again at the dispersion, we see that for palladium, the more damped metal, only the surface wave exists only near the angle of total internal reflection. We can also see the Brewster angle here, where there is no reflection in the double layers, respectively, there is no band gap and a more narrow band gap nearby. In the next video, we will look how to calculate conventional surface plasmons by this program. More information about the presented multi-layer structures that support the long-range propagation of surface plasmons can be found here or in the article given in the video description.